Welcome everyone to the AI Research Roundup. I am Alex, and today we're looking at Darwin Gödel Machine, Open-Ended Evolution of Self-Improving Agents from May 29, 2025. This paper presents the Darwin Gödel Machine, or DGM. It's a system where AI agents, which can use large pre-trained models, learn to improve their own coding abilities. They do this by modifying their own software and then empirically testing these changes on coding benchmarks. These benchmarks are just standardized tests for coding skills. The goal here is continuous, open-ended improvement, much like biological evolution. And if you want to dive deeper into this Darwin Gödel machine, well, the team has actually released the code for this fascinating system. So, in the repository, you'll find everything to run it, including the main scripts like DGM-outer.py, the coding agent, plus directories for prompts, analysis, and benchmark tools. Okay, so this first figure really helps visualize how the Darwin Gödel machine works. We see a cycle here. It starts with an archive on the left, which is basically a growing collection of different versions of the coding agent. From this archive, a parent agent is selected. Then, in this self-modify step, this parent agent tries to improve itself by changing its own code, its own repository or repo. This generates a code diff, which is just a summary of the changes made to the code, creating a new child agent. This new agent is then evaluated on benchmark, meaning it's tested on coding tasks, and if successful, it's added back to the archive, continuing the loop. Alright, so following that iterative cycle we just discussed, these next two charts really show the payoff in performance. We're looking at scores on the SWE-bench on the left and Polyglot on the right. The blue line, our full Darwin Gödel machine, clearly improves over 80 iterations. Crucially, it outperforms the green line, that's the system without self-improvement capabilities, and the yellow line, which lacks open-ended exploration, so it doesn't keep that diverse archive of agents. This shows both features are vital, and the Darwin Gödel machine even gets close to, or surpasses, other strong existing methods shown by those dashed lines. So, this next figure, figure 3, really unpacks that self-improvement process. On the left, the Darwin Gödel machine archive tree for SWE-bench visualizes the agent family tree, showing different evolutionary paths. The graph on the right then tracks SWE-bench scores. We see the average score of all archived agents rising, and more dramatically, the lineage of the final best agent. This lineage shows dips and recoveries, highlighting that open-ended exploration. Plus, it pinpoints specific upgrades, like better file editing or improved ways to generate and rank code changes that cause those big performance jumps. Building on that idea of discovered improvements, figure 4 here demonstrates their transferability. This means we're looking at how well these agent improvements carry over to new situations. The first two charts, model transfer on SWE-bench and on Polyglot, show that the best agent designs discovered by the Darwin Gödel machine still perform really well, even when paired with different underlying foundation models. Those are the large pre-trained models we mentioned earlier. Then, the chart on the right, task transfer on Polyglot, shows that agents trained on Python tasks also perform well on tasks in other languages like Rust or C++. This is great because it means the DGM isn't just over-specializing. That impressive transferability really highlights how the Darwin Gödel machine learns general problem-solving strategies, not just narrow solutions. The core idea, combining continuous self-improvement with that crucial open-ended exploration, seems to be the ticket for creating agents that can genuinely evolve and adapt. This kind of research is super exciting as we move towards more autonomous AI. That's all for this AI Research Roundup. Thanks for listening. I'm Alex.